Okay, so let's start. Since it's 8:16, and others can join in as they go along. Let me just show you my screen. Just give me a heads up if you can see my screen. So, Ishvam, can everyone see my screen?
No.
Yeah, I can see the screen.
Uh, Someone said no, so
Yeah, I cannot see the screen.
just okay. So I'll just stop and restart this. Okay, come on. No, and so yeah. So is it visible now?
No, I cannot see. So what will I do is I will rejoin once because maybe
Yeah, sure.
yeah.
Yeah, okay. So welcome to linear algebra. This is the third lecture, and if you guys have gone through the previous lectures, you'll see that we have covered what's a vector space and
Yes, I can see.
how do we deal with the angle. Okay, so we have seen that how we have dealt with the angles between the vector spaces. We've also seen what is a determinant and a matrix, and we'll be exploring more on that in this session. Right. So we'll start with something called linear mappings. So what is a linear mapping or a linear transformation? So I'll just tell you this briefly, is that let V and W be vector spaces over the same field, and feel free to post questions, right? So even this should be even if a beginner joins the session today, it should be catering to them as well, right? So let V and W be vector spaces over a field. So a field is an algebraic structure with certain laws. I won't be going to that, and we know what's a vector space. A mapping T from V to W is said to be a linear mapping or a linear transformation if it satisfies two properties, and these are T alpha plus beta, which means if I'm plugging in the two values or from the vector spaces, and okay. Uh, Hi Jale, nice to meet you. Nice to have you here again.
Hi.
So
Hello.
so we have yeah. So we just started our session, and we are just going over what's a linear transformation. I think you were there in the previous meeting when this was mentioned, but we'll go over them formally. So alpha and beta be two elements of the vector space, and then if we plug in that to the function that we have defined over here, then we have something which is t of alpha plus t of beta, and we have a t of c of alpha is equal to c of transformation of alpha. Right. And so these can be written in a more condensed way. So, like so. So this is T of A of alpha plus B of beta is equal to A of T alpha plus B of T beta. So something to note. And in math terms, this is called a homomorphism because it preserves the structure or the map between two spaces. That is, this need not be a vector space, or rather, homomorphisms are functions that maps from either one group to another, or either from a field or a ring, or here, for example, we have a vector space. So that's just a fancy way of saying that, okay, so this is a structure preserving map. So the algebraic structures which underline these vector spaces are preserved. So let's just look at some formal examples of a linear transformation. So Okay, so we have the mapping, let's say T R3 to R3, and that's defined by T of x1, x2, x3, and this maps to, I don't know, let's say, okay, so let's map to x1, x2, let's say 0, and that is where where this is x1, x2, and x3 belongs to R3, and this is linear. So we have proved that this is a linear transformation. So how do we do that? We have alpha, let alpha be x1, x2, and x3, and beta be y1, y2, and y3, and this belongs to the vector space of R3. These are two vectors of the vector space R3. So alpha plus beta is equals to x1 plus y1 plus x2 plus y2, x3 plus y3. And we have the transformation of these two going to x1 plus y1, x2 plus y2, and 0 according to this rule over here that we have mapped. And that will give us something of the sort x1, x2, 0 plus y1, y2, uh, oh, okay, this is 0, and this is equal to t of alpha plus t of beta. Right? So similarly for a scalar, let's say we have a scalar here which is belonging to the field of R, and c of alpha is equal to c of x1, c of x2, c of x3, and we have t of c of alpha is equal to c of x1, c of x2, and 0, and this is equal to c of x1, x2, 0, and this is equal to c of t of alpha. So now you can prove how or whether this is a linear transformation. So here we can say that T is a linear transformation, right? So okay, so shall we go ahead and see what's a kernel of a vector space? So a kernel of a vector space is basically if V and W be vector spaces over a field F, let T, the transformation V to W be a linear map. The set of all vectors alpha belonging to V such that T of alpha is equals to theta prime, where theta prime is null in W is said to be the curl of T and is denoted by ker T or an ker T. Now, let's be very honest over here. Since this is a study group and this is not meant to be a formal session, how many of you guys understood exactly what's going on over here?
I had some like linear algebra classes while I was in my first and second year of university, and I read up on it. So like I got at least the gist of it. I got what you wanted to say.
Okay, okay, so how about Jale over here? I think Jale took some references and she read up on this. So do you guys get
Yes,
what
I
she's
can.
getting?
Yes, Turbasu, thank you. I can follow what you're talking about. Yeah, I just
Okay.
before learning about quantum computing, I tried to go over them a few times. Mm,
Mm-hmm.
so I can follow what you're talking about.
How about Prerna and Dipshika?
Yeah, I got it. Like, I have already taken a course on algebra, linear algebra before in my college. Like, in my college, I'm still in my college,
Uh-huh.
in my first year. So I know all these things.
Uh-huh. Okay, so Dipshika is basically a mentor for our Q India. So welcome aboard. And I'm sorry
Great.
there was no formal welcome. There you go.
Nice to meet you,
So,
Deepshika.
okay. So,
Nice to meet you too.
yeah, yeah. So, I'd like Prerna to speak up. Like, this shouldn't be
I
this
did not
difficult,
understand
man.
this part that what is a kernel of a vector space. I'm not aware of this.
Right. Okay. Okay. Can you guys tell me that okay? So we have a transformation and we have the kernel. We've seen what's a kernel, and can anyone tell me that how can we represent this geometrically? Hello, am I audible?
Yes, you're audible.
Yes, you are audible.
Okay. So okay. So I'll just go ahead and help you guys out. So, okay. So this was the boring part. So I wrote that okay. So there's a fun part. So okay, so we have a given coordinates of vectors. So I want to find out where that vector lands. So what we are going to do is that we're going to have some x input and a y input, and that will go to some x output and a y output. That's correct, right? And we want to see where those vectors land, and if we are going to look at these vectors as they are in the transformation, and it turns out that we only need to find out where the basis vectors are. So if we know that where does the basis vectors for these spaces undergoing a transformation lands, then we can find out that okay, so here is where our like ours in a general vector in the vector space gonna land. So I'll show you some examples of this. So consider we have a vector -1, 2, and that can be represented by in a two-dimensional space, and that can be represented by something of the sort v equals -1 plus 2j. I hope this is clear. So how we are doing this, and so now let's apply some linear transformation. So now that we have our the basic fun of our linear transformation is that okay, so whatever we do to the space, we got to have our origin to be kept uh, the same, right? And the grid lines are supposed to be parallel and equally spaced. So these are the two like key like things that you should keep in mind when you're applying a linear transformation. That our origin doesn't go anywhere. Okay. So and our grid line is supposed to be linear, and which means that it's parallel and it's supposed to be equally spaced. So let's look at this. So why this is so and how important are those grid lines? So we'll just see in a moment. So imagine that this same vector over here is being represented on my crooked grid line over here, and so this is my origin of my vector spaces. And here we have this is 2 times of j vector, which is represented by this, and a -1 time of I vector, which is represented by so. Uh, and once we have a linear transformation, say t, and these vectors, whatever happens to them, what we are doing is that we are stretching and shearing these vectors. We're trying to expand these vectors, and we are rotating these vectors. So essentially, the vectors or the bases either get expanded or contracted down, however it wants. But the key point is that the origin doesn't go anywhere, and these lines are parallel and equally spaced. So it turns out that if we do some sort of t, we are getting some sort of a transformed j vector, which happened to be flipped out on its side, and a transformed I vector, which happens to be flipped out on the side again. So let's say I lands on somewhere which is 1 comma -2, which means that the vector over here, this is I capped. Okay, so this is I capped. So this lands on the original. If we draw a grid to the original picture. So we'll be getting something of the form. I'm really sorry for my bad drawing skills. I'm trying to make the best out of freehand. So we see that this vector on the original space, this is essentially 1 comma minus 2. So this is 1 and this is minus 2. This is my transformed I cap, and my transformed j cap has landed on somewhere which is 1 comma minus 2. Oh, okay. So I think we just threw caution to the wind over there. But okay, let's say that it landed on 1 comma minus 2. Okay,
Turbasu,
so
can I ask something?
let's see. Yeah, yeah, absolutely, absolutely.
You said on
While I
top
try to
of
fix
the
this over here.
okay. You said
Yeah, go ahead.
can you go a little bit up to the page over the drawings?
Yeah,
Yeah. You said the grid lines
yeah.
are supposed to be parallel and equally spaced. Does this mean
Right.
we should keep the angle between I and J the same, or mm,
Yeah, so that essentially means so. That's because I'll tell you why, and that's because the angles between I and J, as we seen earlier in the Gram-Schmidt orthogonalization orthonormalization, we have seen that I and J forms a basis, and those are orthogonal basis. So essentially, what that means is that the angle between them will always be 90 degrees, and this is
okay?
why I term this as a homomorphism, is that these structures, which is basically the angles between the vectors, shall in the basis vectors shall be the same, right?
Okay, thank you.
Yeah. So okay, so this becomes somewhere if J lands on 3 comma 0 and I has landed on 1 comma minus 2, and although this does not look like 3 and 0 and 1 minus 2, we'll just take it for that they have landed where they are. Okay, so this means the transformed, so the transform vector is essentially what is basically minus 1, because we had the vector, what was our original vector? Our vector was minus 1 I cap plus 2 times j cap. So this is minus 1 I capped plus 2 times j capped. So this was the original vector. And here the bases have been transformed. So essentially what this means that I and j have been transformed, right? And so we're gonna impute the values for I and j. So what does that mean? That means that okay, so you'll see that j has and I has landed on the the original transformation, like before the transformation, and we see that this is basically on minus 1 1 and minus 2 plus 2 3 and 0, and that gives us with all this computation involved, we have 5 and 2. So as long as we have a record where I and j land on the original matrix, so on the original matrix, we know that what's our transformation. So this is our formula that we were going to find out. That if we had a vector, say I, say x and y, so basically if they were to go over this exact transformation, they're going to land somewhere which is in x of 1 of minus 2 plus y times 3 and 0, and that will give us a general form of our vectors, which is 1x plus 3y and minus 2x plus 0y. Is this clear up till here? Is this clear?
Yeah, it's clear.
So okay, so we want to condense the information over here. So how do we do that? We basically have something called a brilliant little instrument of ours that we called a matrix. And what's a matrix? What this matrix is going to be made out of? And this is going to be made out of, this is where I capped lands. which is our basis vector from the transformed basis, one of the basis vectors, and this is where j cap lands. So as you can, it needs no genius to say that this can be transformed out to any number of vectors, which is 3 cross 3, 5 cross 5, 7 cross 7, or so on and so forth, for higher dimensions, depending on the amount or the number of basis vectors we have. So let's say that this is essentially, so this is the transformation which we have over here, where this is our transformed I cap, and this is our transformed j cap, and we are going to apply that to our vectors. This is our normal unassuming vector, and that's going to give us something which is a transformed vector. This is V transformed, right? I'm extremely sorry. The handwriting is nothing to be proud of, but there you go. So yeah.
No, it's fine. It's fine.
So okay. So okay. So what we have multiple transformations. So if you're going to be having multiple transformations, we're gonna have compositions of these transformations. So first we go over some rotation, and then let's say we go over some rotation and then shift. And first we go over, yeah. So basically, what that's going to mean is that we're going to have a composition of these two transformations, and the rule is to go from right to left. Priya just asked me this exact question: why do we go from right to left this evening? And this was the exact thing that I could come up with. Okay, and that's going to give us V final. So if Prerna is looking for more, in-depth things, so this is where to start. And if you have any doubts or queries, feel free to ask them. Right? Okay. So we have something called a rank of a matrix, if you've heard of them. So what's the rank of a matrix? It's the number of output dimensions. And we call some matrix the full rank if it does not transform to zero vector, right? So how many of you did the Gaussian elimination? Just show of yeses, or
Yeah, I did it.
what was it? The echelon form.
Yeah, I did
the
it.
echelon form.
Yeah, I did it.
Yeah. So
Yeah, I
if
did
we
it too.
can't reduce, yeah, we can't reduce our vectors of the matrix to our echelon form, or if we can't go over to that, the price, the last row becomes zero, or the last couple of rows becomes zero. So what does that mean? That means our matrix is at full rank. Okay, and from a perspective, what does this mean? This means that our entire set of vectors that are being represented by that matrix is gonna go is be called a linearly independent set. And why is this a linearly independent set? Because through Gaussian elimination or through something, what are we essentially doing? We're gonna be reducing this matrix. And what does that mean? That means that we are gonna do some sort of operation, so on and so forth, and we're gonna say that, okay, some of you, I don't know who you are, one of you vectors out here is making me linearly dependent, and I'm gonna kick one of you guys out. So if I'm gonna kick one of you guys out, I need to find out that whether or not these vectors are linearly dependent or independent, as you've seen in the deletion theorem. And if we have found out that one of your vectors are indeed making us linearly dependent, and we want to become that higher independent set of vectors, so we're going to kick one out, and that's essentially what we're doing by reducing a matrix, right? So by reducing this matrix from its by its rank, what we're essentially doing is that for a full rank transformation, we will never be able to get something of this sort. So let's say, okay, so let's say we have some sort of, uh, very crudely drawn pair of grids. So we're gonna make this ft, and this ft, what it does is that it transforms the basis vectors. And what does it do? It basically, what if this just flips it out on the other side? So imagine that we have a function which is essentially flipping it degree by degree or radian by radian until and unless, okay, so we have something of this sort. So this entire plane from our perspective is represented by one line. So what does that mean? That means that whatever was our transformation, it has squished or collapsed our entire plane down to a single line. And what does that mean? That means that our entire, the matrix is essentially not full rank, which means that we are going to be having something which is squishing our set of vectors down to just a single line. And for higher dimensions, we'll be going over through planes. So for 2D, this goes over to one line, and for 3D, it's either it goes to 2D or a one-dimensional line. That's what we mean by when we say that our matrix is not full rank, right? And this entire set, once we get over here, the set of vectors that land on this zero vector, which is essentially this line over here, is called the kernel of T. And essentially, what we have been doing is that we're going to find out whether this is a solution to a set of or equations, systems of equations that we have been doing for so long in our throughout our high school, throughout our college days, so on and so forth. Are we visualizing this yet?
Yes.
Okay. How about the others?
I need to go over them one more time, Turbasu.
Okay. Okay. No problem. No problem. And uh, okay. So if this is more or less, clear, so we can go over to some of the theorems and the formalisms to what I said. So if V and W be vector spaces over field F, let T be a transformation that goes from V to W, be a linear transformation, then the kernel of T is a subspace V. So we have seen that this entire thing is essentially a subspace of our, the V that we are going to we were transforming to. Because essentially, as we have seen over here, is that we are essentially flipping this over a degree by degree. So we are flipping over this space degree by degree, and essentially what we have got is that this straight line. So this straight line is essentially is a subset of the same vector space because it's the same subspace we are flipping over. So just to say, whatever the projection of these of this vector space or this image set may be, we are essentially flipping over that space. So by that logic, we can say that okay, so you have a subspace of V. So another theorem that comes, hands and tied with this. So let V and W be vector spaces over a field F. So let T be a transformation such that kernel of T is theta. Then the images of the linearly independent set vectors are linearly independent in W. So we have the same set of vectors which are independent. And what does that mean? That means that we are essentially have a full rank transformation, which means that all the vectors in them are linearly independent, and we are essentially, since we have the kernel sets to be theta, which means only the origin are in the kernel set, then we see that this entire thing is going over to a linear transformation for a full rank matrix, right? Okay. So a very common question is that okay, so we have seen for 3 cross 3. So this is a 3 cross 3 matrix. We've seen for I don't know 2 cross 2 matrix, and hopefully we have seen or we can see for a 7+7 matrix. So can we scale up or scale down? Which means that if I'm supposed to take something or the other, can we find out whether we're going to take the space from the three-dimensional or two-dimensional space, and we're going to scale this up to a four-dimensional, five-dimensional space? So can we do that? And the answer is that yes, we can. See, matrices need not be square, as we all know. So this is from by the same first principles. This is essentially where I hat lands, and this is where J hat lands, right? And if this is supposed to be full rank, so what do you think that this is supposed to be? For example, where are these base sets of epsilons? But can you give me something whether or not that can you visualize whether this matrix is full rank or not? Okay, so I'll tell you the answer to this, and is essentially not full rank. And how do you visualize this? So we have a three-dimensional set of vectors. So this is a set of vectors which are all what is our nearest possible subsets. So our nearest possible subset is either 2 x 2 or 3 x 3. So essentially, if you're supposed to be going over either of these to be linearly independent, we need to have either a square. Need to have a square matrix for either of these two orders. So if it's not a square matrix, we'll say that they are not essentially full rank for their transformations, right? So can you think of what their input matrix may be? And I've given you guys the hint that the number of columns is equal to the number of rows for multiplication. So the essentially is the number of the columns is essentially, so we have 1 to 2 columns, so our vectors would be A on B, like so. But note that here we have a two-dimensional set of vectors, and essentially this means that we're going to be scaling this down, right? Rather we're going to scale this up, right? So because if we do this multiplication, hopefully under pressure everything works out. So we're going to have something of the order 2 into A, that times 2A, and 0 plus B, so 0B, and that means minus 1A plus B, and minus 2A plus B. So as we see that this is a three-dimensional vector, so that's taking a vector from a two-dimension and making it a three-dimensional vector. So this is how you scale up in vector spaces by using a transform. Is this more or less clear?
Can you please repeat this once again?
Yeah. So just for the sake of it, okay. So we have something over here. So let's just do the multiplication, right? So we have 2A plus 0B, and this means that we have minus 1A plus B and minus 2A plus B. Okay, so this is our so what is this essentially? This is essentially what we have is that our vectors, which were originally two-dimensional, have become three-dimensional. So this is our I cap, J cap, and K cap, and here we have I cap and J cap. So essentially, we are scaling this entire thing up by using our linear transformation over here. Yeah. So is that cool?
Yeah, it's clear. It's clear.
Okay. Okay. So a similar exercise is to do that. What happens when we scale down? So essentially, what we have is that if something is like so, which is a 2 cross 3, vector, and we multiply this by, I don't know. So let's multiply this by a three-dimensional vector, and we're going to see something which is one. So our resultant vector is A and plus 6B plus 8C. I hope that I did that right. And 2A plus 9B 7C. Right? So as we've seen, this is essentially a three-dimensional vector going down to a two-dimensional vector. So is that clear to you guys that what's happening and what's not? Okay, so we've reached a point where
the previous one.
verify, yeah. The previous one in the sense that this matrix.
Yeah.
Okay, so we have a 2 cross 3 transformation. So this is our transformation, right? And we're going to plug some vector in, and we don't know what that vector is, but there's a hint, right? So here's a hint that the number of columns is equal to number of rows for vector or matrix multiplication. So what we're going to do is that we're going to see that, okay, so we have 3 columns, and this is going to be equal to the number of rows. So we're going to need something with a three-dimensional vector. So this is I cap, j cap, and k. So this can be represented by I cap, j cap, and k cap, as we know for a vector representation. It's a column representation of a vector. So okay, so what we get by this this product is that essentially 1a plus 6b 8c and 2a plus 9b plus 7c. So essentially this becomes from I cap, j cap, and k cap. So this becomes I cap, j cap, and k cap. This reduces to I cap and j cap. So here we had 3 basis vectors, and here we had 2 basis vectors. So essentially, we're squeezing it down, and we're squeezing down the entire space to some sort of entity, and where the vectors have become from three-dimensional to two-dimensional. This is clear.
Yeah.
Okay, so we're at this point finally where we need to find out the linear space of linear mappings, which essentially says that these linear mappings form a vector space. So how do we check that? We have seen that for if we have 2 vector spaces over a field F, and we have a transformation. We have 2 transformations from the same VW to V from V to W, and there be 2 linear mappings. We define the sets as T plus S and scalar product CT for C belonging to some field F, and we see that T plus S is well defined and CT is also well defined, like so and like so. And we check that whether these two actually how do we interact these 2 transformations. So we have T plus S, which are the direct sum of 2 linear maps, and thus that becomes T plus S alpha is equal to T alpha plus S alpha, and T plus S beta is equal to T beta plus S beta, and T plus S alpha plus beta, if we just do this entire thing over here and then add these 2, what we will get is that T of alpha T alpha plus beta plus S alpha plus beta, and that means S T of alpha plus T of beta, which is basically that we're going to be like partitioning these 2 with these 2 rules over here, and then we see that we are just going to group these 2 terms over here, and that says that T plus S alpha plus T plus S beta. So this is how defining the sum, the direct sum of 2 linear mappings. And let's say that we have some sort of vector or a scalar P of alpha, then how do we do for the direct sum? So essentially that results in C of T, P T alpha plus P times S of alpha, and that is essentially C of T alpha plus C of T beta of this form, and that is essentially C of T alpha plus beta. So essentially, we see that through all this, that any number of things, t plus s dot dot dot, I don't know, v. So this is essentially linear. And how we say that? Okay, so you say that this we have checked for just two, entities. So how can we infer this for so many entities? So we'll say that since the addition is associative, so this is associative. So we'll just say that the entire thing, we can group this down to like so, and then evaluate. This will form something, and then this will form something, and then group it down, and then we can form some sort of, vectors or some sort of direct sum that correspond to this form. So we have said this is linear. So how do we prove that this is a vector space? So let L be the set of all linear mappings with the domain V and the codomain W, both having the same scalar field F. Let L be the linear space over a field F if the addition and the scalar multiplication be defined like so. Okay, as we have seen in the previous example, like or the previous deduction. Now it's just a matter of verification. Now, if you've gone through that, how do we define, or how do we say whether the field is a vector space or not? We essentially say that t plus s is equal to s plus t is our commutativity, and then we have associativity. Then we have something called a zero, which is a zero map, and that was essentially the set of the identity element. And since we have the identity element, we need to find an inverse map. And what is inverse map? Was that minus t alpha is defined by minus of t alpha, and not necessarily t of inverse. That's not what we're dealing with. Okay. So considering to the scalar field, scalar multiplication, we have c of d times the transformation will give a c of d, the entire thing associativity, and then we have the two distributive laws, and we have the singular identity in F. I think it should be clear to anyone who has gone through how to define vector space. So we have seen here that essentially these form vector space. So if L is a linear space, and the linear space of all linear mappings of with domain V and codomain W is given by some fancy notation again, L of V comma W. And since a linear mapping T from V comma W is also a homomorphism from V comma W, we see that L of V comma W is a set of all homomorphisms from V to W. And this is represented by a fancy notation right here. Right? So is this clear up till this part over here?
Yes.
Okay. So we say that a linear mapping is said to be non-singular. Okay, T is invertible, and in matrix terms, how do we say that? Okay, so if we have a matrix, say for a transformation, we say that this matrix is non-singular. So what does that mean? That means that the determinant of this entire thing exists and is not zero, and that means that if this was denoted by A, so we can find and the A inverse. And in function terms, this is the determinant approach, but in function terms, F is invertible. F for the inverse of F exists if a function, or rather, an inverse of a function exists if we have F is 1 or injective, and we have surjective. If you don't know what that means it's a fancy way of saying that, okay, if we have two sets of vectors from x1 and x2 from the domain set, and fx1 and fx2 from the codomain set, then fx1 is not equal to fx2, x1 is not equal to x2, right? And surjective is that there exists a pre-image of f and for every function. So let V and W be vector spaces over field F of mapping is said to be T is said to be from V to W is said to be an isomorphism. So okay, a fancy new term again. If T is both 1, 1 and on. So essentially it means that if it's bijection. We'll see why do we need that. Okay, so if two finite dimensional vector spaces V and W over a field F isomorphic, if dimension of V is equal to dimension of W, which is that if you're going to be transforming vectors from a domain to a codomain, the vectors will have the same dimensions. And what does that mean? That means that we are doing a full rank linear transformation, right? And that makes more sense in the next theorem, which says that if V and W be finite dimensional vector spaces over a field F with dimension V equals n and dimension W equals m for any m and n, then L V and V to W and m and n are isomorphic, where the set of all homomorphisms from V to W is the linear space over F of all linear mappings of V to W, and Mn is the vector space of all m cross n matrices over field F, right? So essentially, which means that it's a fancy way of saying that, okay, so if you're taking a transformation with full rank, then essentially we are getting something which is of full rank over here. So that means that the dimension of all homomorphisms from V to W is V of Mn, right? So okay, so before we go on to linear operators, we'll see that why isomorphisms are so important. So imagine, let's say, okay, so imagine that we had a transformation over here to a vector, say x, and we don't know what this transformation does, but we know for a fact that this does some weird squiggly things to this vector space. Now, suppose that I don't want this to be transformed. So what do I do? What do I do? I do an inverse transformation, and that essentially means that we are taking, if it's A, then we need to have an A inverse transformation, and we attach it to the vector x, and that will give us this original vector. So this is x transformed. So x transformed. Now, in order for this to exist, we need to have that entire thing to be isomorphic. So what does that mean? That means that whatever this function, if this is from V to W, and this needs to be a bijection, and this bijection essentially ensures that F inverse exists, right? So this is this isomorphic property is essentially important. Okay, so is it clear up till this point? I know I'm going a little fast, but is it clear up to this point?
Yes.
Okay. How about the other guys? We have Rishabh joining us today. Hello. So Rishabh and I had a chat that okay, we're going to do this sometime, and he never joined, probably because of his gate exams. So hi.
Yeah, hi.
Yeah. How are you preparing for the gate exam?
So okay for now. Don't know what will happen. I will talk to you later.
All right.
Like I'll chat with you later.
Yeah, absolutely. So okay, so now we come to a point where we have something called the linear operators, because essentially, remember what we've learned throughout our first course on quantum computing is that every gate is essentially a unitary operator. So we've already seen what does the term unitary mean, and Jale will give us a very nice example of a unitary space right now.
Hilbert space, maybe?
Okay, yeah, absolutely. So any complex valued space is essentially a unitary space where we have
Mhm.
the complex inner product defined, right? So you're right. Okay. So and we have something called a linear operator. So we're going to define the term operator of the term unitary operator here. So all this hullabaloo for this part over here. Right? So a linear mapping from T from the same space to the same space is called a linear operator. From V is going to be transformed to V itself, and this essentially is a linear operator, right? And this essentially forms a linear space by its own right, as we have done this for a special case. Oh, so we have done this for a special case VW. So LVW, and essentially, if that's the case, so we are specializing this entire thing down to LV and V. V is a vector space over a field there. Okay, and the most important part of this case is that we can define another binary composition called multiplication on the set. Right. So how does that work? So let T and S be two linear operators on V, then the composite mapping T2 or rather T compose S. This is the term you can read this as compose or not. I prefer the term compose because of the binary composition. So T compose S and S compose T are both linear operators on V. So note that these two are well defined, right? And we defined it by, let's say, some sort of multiplication, right? This is defined as some sort of multiplication, and since we know that multiplication is a composition from one set to another, we can define it like so, right? So we define S dot T by S compose T, then we have S dot T is from V to V, and then we have this the closure is kind of like this, okay? So now, since we have the composition of linear mappings, we're going to prove that it's associative, and then later on, we're going to prove that whether what happens when, or other, you might skip that part, what happens when these two are commutative, but that's a very good, like point to note for all you math nerds out there. Right. So since the composition of linear mappings is associative, we have, so essentially, can we do say that G, O, F, O, Y, X? So we can say that we're going to solve this first, and then we're going to solve these two first, and then we're going to solve these two first, which essentially says that this is essentially, associative. So we have the mapping IV, which is something which spits out the same value, alpha, and that is called the identity operator, right? So, so an interesting thing to note is that the multiplication with respect to addition is defined as we need to have distributive laws for this entire two things. So we have T dot S plus W is equals to T dot S T dot W, and S plus U dot T is equals to S dot T plus U dot T. So very simple multiplications for, and remember we're dealing with functions over here. And a very nice point to note is that this thing forms a ring with unity. So I'm going to color this over here, right, so that all you math nerds can, get this right. So what's a ring? It's beyond the scope, but it's going to be useful if we're going to be dealing with stuff like polynomial ideals or something like that. But let's not go there. All right. So we have our next definition. I know I'm bombarding stuff away at you right now, and it's kind of like you're being shelled. But if a non-empty set A is said to be an algebra over a field F, so we're defining an algebra. So what's an algebra over a field F? If A is a vector space over F and multiplication of vectors can be done in such a way that A is also a ring in which scalar multiplication satisfies the condition. So, if you heard the term commutative algebra, then essentially I've summed up in one nice sentence, which is utterly confusing, but here I'm pretty sure it's going to make some sense at least. So algebra is an algebraic system, right? Which is a vector space as well as a ring, right? So does that make any sense at all? It's not supposed to make sense to laymen, but it's supposed to make sense here. So does that make some sense?
Could you just explain that ring once again?
Rings are out of the scope, unfortunately. But this, if you look up the concept of a ring, or which you should do is you should go over the concept of a field, because we're dealing with scalar fields, ordered fields over here, and then you can go over the scope of a ring. So that forms an algebraic structure. So a ring is essentially an algebraic structure, and we need to have a unity, and this unity is being defined by like so. So this is our unity operator, right?
Okay. So this
So
this forms a
so we
ring with
have
unit.
something.
Yeah.
Yeah,
So
that
this,
forms
yeah.
which yeah, absolutely.
So this highlighted one, which you said that this green highlighted one, just it forms a ring with unity. So what does it mean? I'm not being able to get the thing that
Yeah.
this.
So essentially, what we're doing is that the unity is essentially once we have defined this composition or this product of linear transformations, then we have something to do. Okay, so we need to find something that spits out the same value. Right? So it's kind of like the identity operator or the identity element, but this is uh, in ring terms or in algebraic terms called the identity with respect to this binary composition over here. And how do we define that over here in our vector space or in our linear spaces is essentially the mapping IV. If you put in alpha, it will give me the same value. So that's the identity operator, right?
Okay, okay.
So does that make some sense?
Yeah, some sense it makes now.
Okay. So so a nice way of looking at it is an algebra. So what is an algebra? An algebra is in an algebraic system. So what this is our algebraic system, which is a vector space, and vector space as well as a ring, right? So an algebra is an algebraic system. There's a vector space, that's a ring. And uh, basically, if here our multiplication commutes, then we have something called a commutative algebra. So if you have gone into things like Grassmann algebra or something like that, you will find that okay, if the algebra commutes, then we can form Grassmann bases out of them. But I'm not going to go into that because that's kind of beyond the scope of this lecture. So, but Grassmann bases should be like it's a very nice way of defining some space when you're scaling up, for example, or generalizing a space. I'm not an expert, but there you go. And next we'll talk about Hilbert spaces, but I'll try touching on some points of Grassmann algebra, but and Clifford algebra if people permit. But let's not go there now. Okay. So T is a linear operator. It needs to be on singular, and T is 1, 1. T is onto. T maps a linearly independent set of vectors V to another linearly independent sets because it's supposed to be an operator. So we are doing a full rank transformation, and T maps the basis of V to another basis, right? So we are essentially doing the same sort of basis, and we are mapping it to some other basis. The basis will obviously be different. Okay. So first things first, can we visualize why T is non-singular? Because because we are defining a set from that vector space to the vector space itself. So in order to be if it's going to be singular, we're going to have something that collapses onto a subset of that vector space, or rather, the dimensionality is going to be reduced. We know that T is 1 to 1 because as we see that we can have inverse operators since we have the inverse Hadamard transform or something of that sort, and we have T is T is onto and 1 1 and onto. So these two are essentially telling us that T is bijective. So T is bijective, and T maps from a linearly independent set of vectors V to another linearly independent set, and that will span another the space V as well. But the other thing is that the basis vectors will obviously be transformed as given in number 5. Okay. So these points are essential. You're going to say that okay, we're dealing with a linear operator over here, right? And we're nearing the end of our talk. And if you have any questions still now, just feel free to shoot them up or something.
I have no questions for now.
Okay. Okay. So we're gonna do something. We're gonna define something else. It's called a linear functional. So what's a linear functional? We've seen. Okay. So briefly, just to recap. So okay. So just tell me what this is. Okay. Sorry, I'm very sorry. So tell me what this is. This is a linear formation, right? And tell me what this is now. It's a linear operator, right? So now we're going to cut some sort of transformation, which essentially gives us from F to a field, and that's supposed to be called a linear functional, right? So a linear functional is a mapping from F cross F to v, from V to F. I'm very sorry, or a linear form is supposed to map from V to F, and we have these two like a vector, a couple of vectors, and that essentially transforms to scalar. So how does that work? We'll get to how that works, but we need to define something called a dual space, right? A collection of all linear functionals on a finite dimensional vector space V is called dual of V and is denoted by V dash or V star. Right. So let's look at some examples. So let's look at some nice examples over here. Okay. So let me think of some real quick. Okay. So let's suppose we have the vectors in in Rn, and we have that represented by as we have in x1, x2, one and so forth till xn, right? And for each vector, we will have a linear functional. They will now exist. Okay, so if this exists, so this is supposed to exist, and I'm pretty sure some of you guys will find this useful or familiar. So for example, a1, a2 to an. And what does that give us? That gives us something of the form, f of x, where x is essentially this entire thing, and this will map on to something like a1, so on and so forth, an, and x1, so on and so forth to xn. And if you do this multiplication, that's going to give us a1 x1 plus a2 x2 plus so on and so forth till an xn, right? So essentially, what does this mean? That this means that this entire thing is the set of all linear combinations are essentially a linear functional, or can be represented by is a linear form, because uh, we have seen why or how does this linearly dependence or linear independence work, but we need to find out why is this linear in the first place. So we see that through this functional, this entire thing is linear, right? So this entire thing is now, we can say that this is a linear form. We're supposed to be covering bilinear forms today, but I don't want to. I don't want to do that. We'll cover that when we are, able to be covering, POVMs or something like that. But positive definite, positive semi-definite, or something like that, because we need to cover, um, I don't know, diagonalization to some extent to go with them. But yeah, so so this is a linear functional. So how do we define this more formally? If I go over, so okay, so let S be a subspace of a linear space V of finite dimension over a field F, and some alpha exists in this V minus S, right? And we now show that there exists a linear functional. So there exists a linear functional on V such that f of alpha is equal to 1 and f of chi or xi is equal to 0 for all xi belonging to S. Right? So how do we do this? Is that we know that, so let dim v equals to n, dim s equals r, which is less than n, and and then we say let alpha 1, alpha 2, so on and so forth, alpha r be a basis of S. And since alpha belongs to V minus S, the set alpha 1, alpha 2, so on and so forth, alpha r, alpha is linearly independent. It may not be a span, but it should be linearly independent, right? Because we're essentially subtracting or taking out some vectors, right? And what this means is that okay, so if n equals r plus 1, this is a basis. So this is a basis of V. Now if n is greater than r plus 1, so if n is greater than r plus 1, we can use the extension theorem and we can extend this to a basis of V, right? And we can, I don't know, term this extended basis as alpha 1, alpha 2, so on and so forth, alpha beta 1, beta n, where r plus 1 plus s is equal to n. Right? So if f be a linear functional, so let f be a linear functional on V such that f of alpha 1 is equal to 0, f of alpha 2 is equal to 0, so on and so forth. F of alpha r is equal to 0, f of alpha is equal to 0, so and f of beta 1 equals 0, since we are essentially extending this and we are terming this as a linear, the basis, right? So this is from here. So f of beta 2 equals 0, so on and so forth. F of beta n, or I don't know, beta n equals 0, right? And alpha 1 or a1, a2, a3, or alpha 1, alpha 2, alpha 3 are, or rather, let me just define this. Okay, I think I did some mistake in the analogy. Okay. So this should be some sort of, since we're extending this, so this should be some sort of scalars, since we're going to be defining this xi, right? And xi, and what is xi? The set of all linear combinations, right? And so we need those a1, a2, ans, right? And a1, a2, ans are arbitrary scalars in S, right? So let f okay, I'll get straight to the point. Let xi belong to some S, this S, and we already know that this xi is given by C1 alpha 1 plus C2 alpha 2 plus so on and so forth plus CR alpha R. Then f of xi, which is our functional, is essentially C1 f of a1 or alpha 1 and plus C2 f of alpha 2, and this all will go to Cn f of alpha n will go to 0. And so we are done. And we have shown that f psi is equal to 0 for all psi belonging to S, and f of alpha is equal to 1, right? Okay, so why was this important? We were important because we're going to look at orthogonal mapping of linear space. Now we're getting somewhere, right? V be a Euclidean space, a linear mapping T V to V is said to be orthogonal on the, if we have two vectors on the set, and T of alpha, T of beta is equal to alpha beta, and for all alpha beta belonging to V, and we need to see that this preserves the inner products. So okay, now we are talking of inner products. Why do we need to talk about inner products? We need to talk about inner products because we are defining orthogonal maps, right? So V be an Euclidean space, a linear mapping T from V to V is orthogonal on V, and for all alpha beta belonging to V. And that means that alpha and beta in itself is equal to 0, so the transformed values will be 0, and norm of T of alpha will be alpha, since it preserves the norm, right? And the distances are preserved, so the norm of T of alpha minus T of beta is equal to alpha plus beta. So as we see seen in the norm, so this essentially is so since we've seen that the norm is essentially a distance, kind of like a distance, so we can see that this is preserving the distance. And some important thing is that T is 1 to 1. And for the last topic, which is essential to this conversation, is that let V be a finite dimensional inner product, and let F be a linear functional on V, then there exists a unique vector x belong to V such that f of V is equal to the inner product for all v belonging to v, right? And this forms the very basics of how do we construct Hilbert spaces and how do we define norms and how do we form the bracket notations. Because essentially remember that whenever we are trying to go over the bracket notations, so let's see, this is alpha, beta. So this is essentially our inner product or standard. So this is our standard inner product in H2, right? And we know that, and due to the Ray's representation theorem, we know that we will have some sort of linear functional that can be represented as the inner product of two vectors in them, right? So that is pretty much it. Rees representation theorem, some proofs of the Rees representation theorem can be, found on Wikipedia. I think that's a good, starter source, and and I'm open to questions.
That unity thing is like ring of unity. That whatever it was like multiplicative, like it's a multiplication kind of thing, right? Like multiplicative
Yes,
inverse,
yes,
right? Yeah. Okay.
yes. You're still stuck on the ring.
Yeah. Okay.
Okay. So I'll give you some materials on the ring aspect of it if you're interested.
Okay.
Okay. Are there any other questions on functionals or something like that? I know the math got a little heavier toward the end, but you know, it's supposed to be like that. It's supposed to be read like this, and it's supposed to be as the physicists have designed this to be, right? So I've tried to, impart that notion, that rigor into this study course. So okay, so let's just streaming right about now. I think we are done for the moment.
Thank you so much, Turbashu. Thank you for the presentation.